So now I'll talk about another type of strain called true strain or logarithmic strain. True strain, or it's also known as a logarithmic strain, and be clear in a bit. So our definition for strain was that strain is a change in length divided by the original length. So the change in length is dl, and the original length is L. Now, as the material starts increasing in length, right, as a result of tension, dl is changing clearly, but L is also changing. So if you want to find the total strain right from the point where you started stretching it, then you need to take the integral of this quantity from the original length to the current length, whatever it is right now. But the integral of 1 divided by L is log or natural log of L, and then you put in the limits, and you get log L divided by L0. So this term now is called the true strain. It's true because that's really the right way to compute the strain, because that integral now accounts for the fact that the original length in the denominator keeps changing as you stretch the material. So the expression for the true strain is natural log L divided by L0. Okay, so when it's a natural log, it's to the base E, the exponent. So on the top, what you see is a plot of the true stress. The true stress is the same as the original one. It's basically force divided by the cross-sectional area. And on the x-axis, you see the true strain, which is now the log of the length divided by the original length. So you might say that looks very similar to the previous plot. However, there are two differences. One is, well, there's one major difference, which is that U and F are at different locations for true strain. So if you go back to the figure, and I'll redraw it here, if you looked at the plot of sigma versus strain, which is the engineering strain, you saw that the curve is like this, where this is the ultimate strength, and this is where it fails, right? This is the failure stress. This is the stress for ultimate strength. And so here you see that the ultimate strength point is below the sigma F. Okay, that's just because the way we computed the strain, or the place where we would see interesting behaviors. So that's something to note. Okay. The stress doesn't change. It's the same point. What happens is we are recomputing the x-axis. It's being rescaled because now using log versus using the engineering strain. And so that's something to remember. If you see sigma F is greater than sigma U, then it's probably because you use this kind of depiction to find the strength at which different things, interesting things happen. Okay, for engineering, this is different from stress strain curve, which has SU is greater than SF. So I'll just show the SU here, SF here. Okay, so I've shown it for you on this plot when you read this again. Okay, so normally we don't bother with this plot. We just go with the other one. I just wanted to know that there's another strain, which is probably more accurate way of computing the strain, which goes by the log. Okay, so we talked about a specimen which is loaded in tension, like you fold it. You could do some other tests which are, so this test is good if you're going to use that material in, say, an element, machine element which is subject to tension. But many things are not subject to tension, they're subject to compression. Like, for example, this beam here, it's subject to a compression because it's being loaded from top. So then we can do a test with compression, which will be very similar to the one I showed you, except that the force there is not going to be stretching it, but compressing it. So then in this case, you will have something like this. The force is, as I've shown, compressive. The issue with this kind of test is that, so what we're trying to do is we're going to stretch the material till it breaks, right? And that's a nice thing, because if you do it the other way, which is compression, there's a possibility that before it breaks in compression, it'll actually buckle and break that way. And that's not a mode we want to have in this test, because we are not looking at buckling failure. We're looking at failure due to compression. So we need to take care as the specimen might buckle. So that's a totally different mode of failure. So what people do is they normally don't do a test in compression. What they do is they do the tension test. And it's noted that the curve you get in tension is similar to the curve you get in compression. So why bother? Just make a tension test. The curve for tension compression is similar to tension. And so just stick with the tension test. Now, there are materials where they would behave very different in compression versus tension. Okay. So most of the building material, reinforced concrete, that's behave very differently in compression. It's actually stronger in compression than in tension. So you never have these things bearing tension. But for materials like steel and all, you can just assume that the curve is the same. So that's one type of test. The other test which people are interested in is the torsion test. Okay, sometimes you have things which are subjected to torsion, like usually rotary things are subjected to torsions, and that leads to shear stress, and you want to ensure that things don't break in shear. So what you do here is you take a specimen now, which is usually a cylindrical, and then you load it with a torque. So tau is the torque. And let's say the specimen length is L0. And then if you look at a cross section, so I'm going to blow this up a little bit. So if you look at the cross section, okay, when there's no tension, if you draw a line from the center to this point, let's call that C, due to the torsional load or torque, you see that this C point will move to this point C prime, and the angle swept here, let's say that is gamma. So then what you can do is you can define, well, this is an empirical formula which I will derive some point of time in the later chapters, which relates the torque, tau. Let's write it down later, tau equals G, which is the modulus of rigidity. Modulus of rigidity of material stiffness, r theta divided by L, where r is the radius of this cylinder. Okay, so you can think of, yeah.
Would that theta be the gamma that you put down?
Oh, my bad, my bad. Just check, stick to one notation. Yeah, let's just stick with theta, just because my gamma looks so much like my R, and then it's going to be confusion. Let's just stick with theta. Okay, so you can think of this R theta as the arc length, right? So if you have a circle, and then it sweeps an angle theta, then this sweep is S, which is arc length, is R theta, right? And so that's the arc length divided by the length of the cylinder. So again, tau is the torque, L0 is the length, R is the radius, theta is the angle swept when loaded, and then G, which is basically which is similar to the Young's modulus for tension test, is called the material stiffness, or it goes by the name shear modulus, or it also goes by the name modulus of rigidity. Okay, my bad. This is actually not the torque. This should be the torsional stress. So if you do the units, then that will be more appropriate. So just correct that torsional stress, tau. In fact, we'll use the notation T for torque. So it turns out that the stress is also related to the torque in the following way. The stress, which is torsional stress, is T, which is the torque, times R divided by J, and I'll define what J is. Okay. T is the torque, J is the polar moment of inertia, so the second moment of area of cross section, or its polar moment of inertia. It's called polar inertia. Is actually a function of only the geometry of the cross section. So in this case, it's a circular cross section. So the formula is pi r raised to 4 divided by 2. Function of geometry.
That's the r to the negative 4.
It's positive 4. And we'll come back to this probably a little later. So if you want to have, for the same torque, if you want to have less shear stress, then you want to have a high J, right? Because it's inversely proportional to torque. Okay, so that's so coming to the test, what you can do is now similar to the tension test, you can keep increasing torque. Okay, that will increase the shear stress, right? Torque is proportional to the shear stress, and that shear stress will cause that angle theta to increase. Eventually, this material will break in shear, so it'll break when one surface and another surface are, you'll see a crack which is along the cross section. And then you can do the same plot which we did earlier, a plot of shear stress now versus theta, because theta defines our angle turn, and that's like the shear equivalent of the strain, longitudinal strain. So then you'll see that the curve looks very similar. with a stress U called the ultimate shear strength. And then this strength so that corresponds to a torque TU. You can find the ultimate strength SU, which is TU R divided by J. The same formula I used earlier, except that I'm replacing the torque with the ultimate torque. So this is the strength at which it breaks. If you like, you can just change this to SU, which is also is one of the ways in which you can quantify how strong a material is to shear stress. So really, we see that we get same behavior. However, you need to find the modulus of rigidity and get those slopes and so on. So you can't escape this. You have to do this test. Unlike compression, where you can assume that tension and compression, we have the same curve. Questions? Okay, more theory. So that's one thing we're interested in how things break due to a force. But then there are other applications where we're interested in energy absorbing mechanisms in materials. So for example, in a car crash, right, you want to have the front part of your car has to be able to absorb the energy so that it doesn't really transmit it to the occupants of the car. So that's where you have metrics for how well the material can take collision. So this is known as the energy absorbing. So two things here within energy absorbing characteristics, and I'll define them in a bit. What's that? I'm short of a word.
Maybe traits would be a shorter word than characteristics.
Oh,
I see. All that out.
I see. Yeah. Thank you. So, that's fine. So there's something called modulus of resilience, and then there is modulus of toughness, and we'll define both of them. They for us, it means the same, right? To be resilient and tough. But in case of materials, they are different because they're different in different regimes of the stress strain curve, and that's how we'll distinguish them. So let's talk about resilience. This is the first one. So resilience is defined as the capacity of a material to absorb energy clearly, but within its elastic range. Okay. In fact, that is what is going to set it apart from toughness. So I'll underline that. So that's the key. And so we have what is known as a modulus of resilience. And we'll denote it by U underscore R. It's the energy absorbed per unit volume. It's within the elastic range. Okay, so when we look at the curve for a material, when we did the tension test, it would look like this, right? So what we are interested in is only up to the elastic range. So we look at the yield point. So if you recap, if you go back to lecture 4, okay, so we had the yield point. Okay, and after that, the curve starts becoming non-linear. And so we want to focus our attention till that point, and we want to find the energy using that particular point. So I'm looking at the yield point. So go back and maybe just try it a little below. So let's say that's the yield point. And there's a strain at this yield point. Let's call it with a subscript y, so epsilon y. So what we want to do here is find the energy. The units of energy are, well, it's half mv square mgh. But if you want to find it in terms of stress and strain, the stress times strain is actually a measure of the energy. So what we need to do effectively is to find the area under this curve up till the elastic range. So this is basically the energy within elastic range. Okay, and this is, by the way, the yield point. So what we'll do is we'll make this assumption that this thing here looks like a triangle. This is a triangle. Okay, so it's clear that these two sides are horizontal vertical, but then that curve here is actually a straight line. Okay, which is probably true to an extent, but maybe there's a slight curving, but we won't really bother. So if you assume that's a triangle, we just have to find the area of a triangle, and the area of a triangle is half base times height. So UR is half base times height. Okay, so it turns out that the area under the curve is actually energy per unit volume. Okay, so if you want to find the total energy, you just have to multiply the volume of the material. So half the base is the strain, the height is SY. But when we know that the strain is stress, in this case, it's the stress is the strength here, the yield strength, divided by the Young's modulus, we call it E, times SY. So the modulus of resilience is half SY squared divided by E. Okay, so key thing is we looked at the area under the stress strain curve within the elastic range. Okay, so now let's move on to the modulus of toughness. So what's toughness? So it's the second measure of energy carrying capacity. So it has defined the ability to absorb energy without fracture. So we have a modulus of toughness which will denote as U underscore T. And we'll define that as the energy for energy absorbed per unit volume without fracture.
So the ones you have with fracture in like that.
Oh, sorry. Good catch. It's without fracture. So you don't want it to break before you compute that. So just like the previous one, what you do is you look at the stress strain curve, but you look at not at yield point, but you look at the fracture point. So let's draw the stress strain curve. Go back and you can view this. So that's the fracture point. So I need to draw that curve up to the fracture point. It goes up to the maximum and it dips down. And so this point is our fracture point. Let's say that's the ultimate strength. So approximately this point here is, so that fracture point, we don't really know. We draw a line here. Sy, this is the yield point. This is the fracture point. Then this is the ultimate strength. Okay, so now what we need to do is, just like previous case, we need to find the area under the curve. So let's shade it first. So this. That's the area under the curve. Okay, so what we do here is we make another assumption that in order to find this area under the curve, we are basically assuming that it's basically, we take the average of these two values, SU and SY. And so let's say that is about here. Half SU plus SY. And so what we're doing effectively is sort of drawing a triangle, sorry, a rectangle. This actually line is a little below, it's not so high. So it looks like this is a large area, but it's actually not, because if you look at the curve, this area is sort of, so if you draw it somewhere midway like this, then you sort of miss some area here, which, so when you find the area under this rectangle, all this area, you miss out some area here, but then you're counting for this area. If you take it and you put it over here, you get approximately a rectangle, and this is like a gross estimation of how we might compute the area. So it's highly approximate, but that's okay. So we just say that the area is, so UT is base into height, because that's the area of a rectangle. The base is EF, the height is the average of SU plus SY. And so the formula for UT is SY plus SU divided by 2 times EF. So as long as you do this consistently for all materials, you will get a measure which is consistent. Okay, so you don't really have to worry about the fact that it's a gross estimation of the area under that curve. Have you done this before in strength of materials? Probably learned this. Okay, so this is just a review. We'll get to more tougher things as we proceed, but this is like the core of what we do in design is to use these terms, these measures to do useful things. Okay, the next thing in our list of prereqs which we need to know is hardness. So this is section 2.5 on hardness. Right, so the property of a material to bear penetration is basically the hardness. So it's defined as the resistance of a material to penetration by a pointed tool. Now the measures for this are pretty much empirical, or measures or tests. One of them is known as the Rockwell hardness test. This is the one used by the standard ASTM. So these are some of the standards and codes. If you go back, they use the Rockwell hardness test. And there's another one which is common, which is not the Brinell hardness test. Okay, so let's briefly talk about these two. The first one, the Rockwell hardness test. Okay, how is it done and what comes out of it? Well, so the way this is done is you take a specimen. Okay, whatever it is, it could be a cam, it could be a machine element, shaft, whatever. It goes into a machine which has which is a head which has a diamond indenter. So that's our diamond indenter. By the way, diamond is very hard, right? So what you do here is you apply a force. Let me call that F. The first step is, and this is the specimen or the specimen whose hardness you want to find. So the first step, let's call that A, is apply F equal to about 10 kg. Okay, so 10 kg is so 10 kg is not the force. You need to multiply that with gravity to find the force. It's about 100 newtons, right? And then once you apply that force, what you'll see is that the indenter goes down to a depth. Let's call that 1. So this 1. So that's note the depth 1. Okay, so then what you do is you increase the force to 140 kilograms. So you keep F1 applied, but you apply additional force. Let's call it 1, F2 equals 140 kgs. And so when you apply a new force, you will see that the indenter has gone further down. That's called 2. So note the depth 2. Okay, so once you're done with that, remove F2, but keep F1 applied. So now when you release F2 and keep F1 applied, you'll see that the indenter goes back a little bit distance. So now you should note the depth 3. So the depth has changed, in fact, because it's gone up because you removed the force F2. Okay, now measure the distance between 1 and 3. Okay, so 1 and 3 are the depths produced by F1 only, right? But the reason why they're different is because in one case it was there was no F2. In another case, there was F2 which was applied and then left removed, which is the case of 3. And so that distance is, let's say, E. Then the Rockwell hardness number, it's also known as HRC, is 0.2 minus C times 500. I have no idea how those numbers came up, but as long as you do the same, consistently the same thing with all materials, you should see that you get consistent numbers. And this is really not, these are not like, these are relative measures, right? So when you look at a material and if you say the HRC is 200, you can make no sense of that. The only way you can make sense of it is if you know there's a very hard material, let's say it's diamond, and if its HRC is 500, and then if you have material which is 200, then you can say, okay, it's going to be much softer than diamond. That's how you make sense of it. It's always relative, it's not absolute. So what gets multiplied really is not a big deal. What matters is that it's used in a way which is comparing it with something else. Okay, so that's the Rockwell hardness. One thing to note is it is based on the difference in depths. Okay, and the next one is actually different from this one in terms of what measure is used. The Brinell hardness test Okay, so here what you've done is you have a press which has an indenter, which is actually not shaped like a pointed tool. It's actually a spherical indenter. I don't somehow have what material it's made out of. Maybe some very hard material, but it's not diamond. And then there's the specimen. And this test is much simpler because what you do is apply a force. And I think the force depends on what force. The force really depends on the type of Brinell test you do. It's like different tests have different forces you apply. So apply force, okay, which comes from a specification sheet. And then what that does is it basically indents the surface So if you have a top view of this, then you see that it's basically a circle. It probably has a diameter less than the diameter of the spherical indenter because it didn't fully penetrate. And that really is how you determine the force. You can't really have a big force because then So some materials will have a small force, some will have big force, and that really determines on the material you're testing, because if you have too big a force, then that indent is just going to go inside, and that doesn't make too much sense. So if this is D1, then this D2 is less than D1, and that's usually the outcome. If you don't see that's true, then you probably need to change the force. Okay, so what you do is you find the diameter, find D2, and hence area associated with the indentation. Okay, let's call that A. So then your Fresnel hardness HB is the test force divided by the surface area. Okay, which is A, the indentation area. So the good thing about this particular measure is that it has units of force per areas, or Newton per meter square, or it is units of stress, right? Force divided by area. However, we never really say that the hardness is Newton per meter square or pascals or whatever you like. We just call it HB. That's the typical way to call it. And that's basically what is used to figure out if something is harder than something else. Now, the good thing about this one is I think it's simple. It has a good correlation with ultimate strength. And that's not surprising, because that has actually units of force per meter square, right? And so that's one is usually the preferred one. It's also actually kind of simpler to do the Fresnel test than to do the Rockwell test. It's much easier to see that indentation. You can just use a camera to figure out what that area is. Okay, if you it's usually easier visually than it is for the other test where you trying to find the depth.